Alrighty. Well, welcome to the 6 of you that are in person today. 7 now. Awesome. Thanks for being here. First, I lost my train of thought. What was it? Oh, don't forget to do your quiz 3. There was a problem with it on Canvas, but that's been fixed. So I changed the due date to Saturday at midnight instead of today at midnight, just because of that error. So keep that in mind. Also, next Friday, we're going to have our exam 2. So get to studying for that. Exam 2 should be covering tsunamis, volcanoes, and it will probably cover flooding as well. So keep that in mind and get ready for that. So that's coming up next week. If you're missing any of your assignments on Canvas, if you see that stuff isn't graded, it's because I don't have it yet. Except for your second in-class project, I'm going to be finishing up grading those today. So keep that in mind. Get those assignments in, check the due dates on those. If you need an extension, let me know. Just keep in mind, there are only 2 weeks left to the winter session, so we're almost done. So the sooner you get those in, the better for both you and me. So that'll make it easier on all of us. All righty, so yesterday we were talking about river systems and how dynamic they are, different zones of the river system. Zone 1, where you have erosion. Zone 2, transport. Zone 3, near the mouth of the river, deposition. And then we started talking about discharge, calculating discharge. Discharge being the volume of water per unit time flowing through a river system. How much water can that river system take? How much water can it transport? And as you can imagine, more water means more stuff can get mixed up with it. We also talked about bank full stage, bank full discharge, overbank flow, and how those are important terms to use whenever we're talking about flooding specifically. Okay. So we were looking at a couple of these. These are hydrographs. Hydrographs are just measurements of different stages at a certain stream gauging site. These are all over the country. There's a huge network of thousands of these gauging stations that the USGS uses to monitor streams, and they give us a lot of really good data, really pretty accurate data as well. So originally we were talking about how, right when we left off, we were talking about how stage height and discharge are related, how they have a similar shape during a flood event. So on the right, we have the stage, which is just the height of the water measured from the bottom of the channel. On the left, we have discharge, the actual volume in cubic feet per second traveling through the channel. They have a very similar shape. So instead of, remember how we have to calculate discharge, we have to measure the cross-sectional area, so the width, the depth, and then we also have to measure the velocity all along that channel, average that out to give us a good velocity. So that takes a lot of time. That's very time consuming. It's very expensive. So if we can find a way and develop a way to relate just the gauge height to the discharge, that's going to save us a lot of time. It's really easy to measure the depth of something. It's just one dimension that we're measuring. So if we're only measuring one dimension, it's really easy to record that, and then from there we can calculate discharge and know a lot more about the river system. So that's where this rating curve comes in. And you're going to be working with these in lab frequently. So basically a rating curve is this curve on this graph relates the gauge height to the discharge. So let's say we have a gauge height of 10 feet. So our y-axis is our gauge height. If we go from 10 feet, we go all the way over to where that 10 feet intersects that rating curve. You go all the way down to the bottom there, and it looks like that's going to be 3,000 cubic feet per second in discharge. So the rating curve is just everywhere along that line. That's where the corresponding gauge height corresponds to a certain discharge. So that's how we're going to use this. So if we're gonna try to interpret this rating curve. So what's the stage going to be when the discharge is at 5,000 cubic feet per second? So we know the discharge, we're trying to find the stage. So it's hard to do in person here, just because it's so far away, but if we look at 5,000, right between 4 and 6,000, we could go up to the rating curve. What's that gonna be? Who has an answer for me? C, 11.5, that looks about right. That's correct. So really simple tool. Each of these is developed for a specific stream gauging site. So after you run all your calculations, you develop this rating curve, and then from there you can run a program that'll automatically calculate this for you based on whatever gauge height that your gauging station is giving you. So each of these gauging stations and each of these creeks gives you its own rating curve. So it's unique to each site. Okay, so when we're talking about discharge, we're talking about a volume of water. So what contributes to discharge? So obviously precipitation. All rain is going to really charge these rivers, and that's what's going to give us discharge. So as you can imagine, more precipitation means you get a higher discharge. That just makes sense. If you don't have a lot of rain, you're not going to get much discharge. We also have something called runoff, which we've talked about yesterday. Runoff is just all of that overland flow that's not related to any channels. So anything that just flows on the land and down into a stream, that's runoff. So, but we can also get stuff like infiltration. We talked about infiltration. That's where we have enough low velocity where the water is going to seep into the soil. So in areas where we have lots of grass, forests, we're going to get a lot of infiltration. There's not a lot of slopes and free slopes where the water can flow. So all that friction from the grasses, from the forested floor is going to slow that down. Yeah.
For infiltration, what's the best groundwater you can get in the world? So there's the Rockies, there's here, you can do natural spring. The best.
The best ground. What do you? So are you talking about the water quality itself?
Yeah.
Okay, that's a good question. Huh.
For the best environment.
The best environment to get, I would probably say grasslands and forests, mainly because all that vegetation is going to soak in some water and distribute some other water into the groundwater system. So the water that gets soaked in, it's going to take in any hazardous materials, any contaminants, and remove that from the system. So you're probably going to get a better quality water. I am biased. I think Pennsylvania water is quite good, mainly because of the tap water taste. And that's because it has a really high mineral count. So if some of you have had hard water where you have to get a water softener, because you have that buildup of minerals in your pipes, those minerals are actually really good for you. There's a lot of calcium, good for your bones, just by drinking that tap water. So the mineral composition comes from what happens when it's in the ground. So that can be more geologically based. So if you have limestone areas, more sedimentary rock where that water can get almost filtered through sandstone, that gives you pretty good quality groundwater. Yeah, no problem. That's a great question. So that's infiltration, where we're soaking into the soil. Interception, that's where we're talking about plants, vegetation, where they're going to soak in some of that water that gets infiltrated. They can also just catch it from the leaves itself, and that can, if it sticks to the leaves, it'll eventually just get evaporated, so it won't enter the river system. We can also have human elements that are intercepting it. So dams, retaining ponds, stormwater management. This is all going to catch water in different ways and send it somewhere else. And that could be, usually that ends up in a stream at some point, different from where you want all that water to accumulate. So stormwater management is really important here. And of course, evaporation, that's going to be a negative effect to discharge. We're taking stuff away. So evaporation is always happening, and that's based on temperature and dew point in the air and humidity. So as we have discharge coming in, we're going to have evaporation taking stuff out. Yes? Some of them have more of a negative effect than most. So evaporation, definitely, because we're going to take stuff out of it. Interception is, it's going to delay the entry into the stream channel. So it's going to divert it. It's going to end up in the stream at some point, but we're going to take it away at a point where we don't want flooding. So it's a negative in the immediate area. It's going to be a positive in the grand general scheme of things, because it's still going to get into the stream system. Infiltration, it's going to be a positive, but the rate is going to be so slow that it's almost negligible, just because it's soaking in. There's a really good graph on, or image for groundwater sources based on distance from the stream and depth in the actual ground for how long it takes to reach a stream. So like if you had a drop of water at a certain point, so like if you infiltrate right next to the river, maybe you're going to get into the river in a couple of days. If you infiltrate up at the headlands, you're probably going to get to the river in 1,000 years. That's how slow groundwater moves. Very slow, but they do get a lot of recharge from certain stream situations too. And something to keep in mind, that streams also are going to infiltrate. So if we have on this image right here, you can see the groundwater water table that lines up with the top of that river. If we have a drought and we don't have a lot of precipitation feeding into that river system, that groundwater table is going to decrease. It's going to decrease in its elevation. So eventually, instead of the stream gaining from the groundwater, the groundwater is going to end up gaining from the stream. So the stream itself is going to infiltrate and into the groundwater system. So the stream is really based on where that water table is underground. So that's a really important component. Now, the groundwater isn't really going to contribute to our flooding risk because it moves so slow. So whenever we're talking about flooding risk and the actual hazard behind it, we care about precipitation and the actual stream itself. So all that infiltration from the stream itself is really negligible. So this is just the test from this River Research and Design way back in 2008. They're testing precipitation along this construction zone. I hate the music they chose for this video. So this construction zone is just this gully built right next to a highway, and we're taking a very long exposure video of where all of this water is coming from. So they have a dam up at the front. All the water that feeds into this is coming right from the pavement. So during our greatest amount of precipitation, our rainfall peak was way back here, but there's a delay in between the max discharge coming out of the river and the peak discharge of precipitation. So, and that difference is called the lag time. So with each precipitation event, you're going to get a lot of precipitation all at once, and eventually that river system is going to catch up to it. And so basically you can tell graphically when rain started and when rain stopped based on a hydrograph. But most of this water came right from the pavement. This channel goes all the way up there, but all of that just washed over as runoff right into this little channel here. So yeah, geologists are really fond of construction sites just because we can do many little experiments like this, where a lot of the components are controlled. There's no vegetation here. We all know the soil type. We can pretty much map it out really easily. So it's pretty much at every construction site, you'll have geologists filming stuff like a bunch of weirdos. Yeah. So just like I said, lag time, discrepancy between the peak precipitation and peak discharge. As soon as you have rain, it's not all going to get into the stream at once. We have some stuff landing outside of the stream. That watershed is going to catch everything, and eventually it's going to come into the stream right at our gauging station. So that lag time is the time where we get the most rainfall, and then where we see all of that rainfall in our gauging station. So it's that time difference between the two. And there's always going to be a lag unless you have, let's say you put a hose right at the gauging station and you just started pumping water into it. You would see that immediately. There would be zero lag time. But because that's not what we're doing, we have a storm over a large area, over our watershed, catching all of that water. It's going to flow at different rates. So that's why you see a slight increase as the rainfall is beginning, but you don't get the peak until long afterwards, because all that water has finally entered the stream and its discharge, and then we get that gradual decline in the discharge. So the amount of lag time that we get can tell us a lot about the watershed itself and the drainage basin as a whole. So if we have a short lag time, that means we have some really fast and furious rain, huge amount of precipitation, and the amount of precipitation is a lot faster than the rate of infiltration. So that means we're getting a lot of runoff, all of that overwash, that sheet flow on the surface. That's going to go right into the stream very quickly, very rapidly, and we're going to see that reflected in our hydrograph. So if we have poor interception, meaning we don't have a lot of vegetation, if we have a lot of urbanization, all those parking lots, those I'm blanking on the word. Yeah, parking lots, stuff that's going to block that infiltration, roads, any paved surface. So you have all these barriers that are going to stop infiltration. It's going to flow into the stream system a lot faster. If you have a short lag time and you have poor infiltration, you're going to get a huge rise in your discharge very, very fast. So the river system may not be able to distribute it effectively. So this is in the case where we get stuff like flash floods. So if we have a longer lag time, that means we have more of a sluggish catchment. So we have maybe a slower rain, not so much precipitation. So we're going to get more infiltration if we have like a real nice porous soil. And let's say it's pretty dry, so it can absorb a lot of it. Eventually, if soil gets saturated, it's not going to absorb any water. So that's when you get the runoff. But if you have really porous, really dry soil, that's where you're going to get the most amount of infiltration. And if we have a lot of vegetation, a lot of woods, grasses, retaining ponds, that's human influence in stormwater management. Those are just areas where we can catch a lot of water, where we draw all that water from our impervious surfaces. That was the word I was thinking of. Impervious surfaces like pavements and parking lots. All that water is going to flow into a retaining pond where it's not moving around. It's just going to sink and infiltrate down into the soil. So we're going to prevent flooding just by getting water to where it's going to stay and then infiltrate. It's a really easy, really effective way of mitigating flood damage. So we talked about overbank flow and how each stream channel has a certain capacity, and that capacity is defined by the height of its channel walls. We can have bank full discharge, where the water level matches the height of those channels. And then we can have overbank discharge, where we have complete flooding, overflow of the channel walls. So this is a town in Iowa that got hammered pretty quick right on the Missouri River. Railroad crossing sign is probably 8 feet tall, so that's like 6 feet of water below it. So that's a pretty devastating thing. Okay, so something to keep in mind with flooding is that everyone should expect flooding. If you live near a river, unless you live in, actually, even if you live in Death Valley, you should expect flooding. It happens at every single stream, it happens everywhere, and it is unavoidable. You cannot control the weather. We've tried controlling the weather before, and we can't do it, but what we can do is make it rain more. So cloud seeding is a thing that we can do. If you do, what is it? Silver iodine, I think, yeah. If you basically fly overhead in a plane, dump silver iodide out of the plane, it creates a lot of rain, a lot more, bigger volume. It's going to dump out all of its precipitation like all at once. So that was developed during the Cold War, I think, back when the military was trying all these crazy things to fight the Russians. But we can't stop rain at all. So this is that same town in Iowa. They've been recovering for a very, very long time, just from this one flood. So it took about 180 days for the flood water to drain, just drain and get away from its regular levels. This home right here is about 100 years old and it's completely ruined. All the wood is waterlogged and it's not replaceable really. Once you get down into the foundation, you're living in a house that's condemned. This is another view of that property. It had a lot of farmland in the back here. All of that is ruined the entire crop yield for that year. So, and as you can imagine, if you're a farmer, you rely on a year's worth of crops quite a bit. So that you get a lot of economic disparity, mainly because you can't really grow in saturated soil like that. It's impossible. Okay, we've seen this before. Just to reiterate, we have bank full stage, where the height of the river matches the height of the banks, and then over bank stage, where we have flooding, overflow of the channel banks. This is where we get flood discharge. Anytime it goes over that that capacity limit. Okay, so these are the main causes of a flood. The biggest thing, obviously, is precipitation. You have to have some massive input of water in order to have a flood. If we don't have a lot of precipitation, we're not going to get a flood. So, and this can come from just regular rain. It can come from hurricanes. I know some of you in the class have dealt with Hurricane Sandy coming up the coast of New Jersey. Those can definitely bring in lots and lots of precipitation, and that's going to give you a huge amount of flooding. If you have warmer than average temperatures and you live in an area that is used to more stable snowpack, if you melt all of that snow all at once, then you're going to get a pretty severe flood. That's usually snow melt we're not able to account for it because we can't really measure it if it's just staying where it is. We can also get in areas where you have a lot of permafrost, where the ground is frozen solid. Those are areas where you're not going to get infiltration. So if you can't get infiltration, even though they have pretty normal soil, it's all locked up almost like brick because of the water content and the ice content. So if you can't get any infiltration, as we've seen, you're going to get more inflow into the stream system. That's going to rise the discharge up over the banks. And then, of course, human causes, because sometimes we can't get stuff right, like dams or levees. So if we do any poor engineering, if we don't update and maintain these engineering and infrastructures, we're not going to properly prevent these floods. So as per usual, floods are the #1 disaster in the US. Everyone has experienced them all over the country at some point. So based on this flood risk map made by NOAA, we have below average, above average, and high risk for flooding. And every single state, even Hawaii and Alaska, have experienced flooding in the last 5 years. So let's take a look at where we are. We have an above average flood risk here in Delaware, and that should probably make sense. We're a coastal state. Even though we're in Newark, we're in Newcastle County, which is a lot higher in elevation. We're still at a more lower point than some places upstream. We're also, the closest stream is White Clay Creek. White Clay Creek is actually a very, very big watershed. A lot of it is in Pennsylvania. So if Pennsylvania gets a lot of rain, we're going to get all of that discharge coming down the White Clay Creek. And as I'm sure some of you have realized, White Clay Creek is not a very deep channel. So it's very easy for stuff to flow out over the top of White Clay Creek there. So why would it be that this region up in Minnesota and the Dakotas and Iowa, why do they have such a high risk for flooding? What do you guys think? Think about those regions. What's their climate like? It's cold. So what do you think? What do you think they have a lot of in their soil? Ice. That's right. So if we have a lot of ice in our soil, we're basically creating a parking lot. We have no way of getting water to infiltrate into the system. And since they have this is big farming territory. Iowa is just nothing but cornfields as far as the eye can see, but it's still very cold. So if you have just fields and fields and fields of permafrost, you basically have several acre wide parking lot. So you're going to get a lot of sheet wash, some runoff, and you're not going to get any infiltration. So that's why Iowa, Minnesota, the Dakotas, they get a lot of flooding. The average temperature in this area is 20 to 30 from probably November to March. So that's a long period of time to have those really low temperatures. And that's also where that period of time where they get a lot of precipitation. Okay, so we're going to break down floods based on zones now and what those floods look like in each of those zones. So remember, zone 1, this is our headwaters. This is where we have erosion. We're removing material. We have a very steep gradient, very steep channel walls. So because of that, we're going to have a very small capacity. Because of the steep channel walls, the water is going to rise really quickly in the channel as a whole if we get a lot of rain all at once. So because we're up in the mountains, think of the Appalachians, that's more rock, that's more stone. So you're not going to get infiltration, quick infiltration, like you would with sediment or soil. So you're not going to get any infiltration, and you're going to get a lot of precipitation. Basically, it's just going to flow down the chute as fast as it can. It has a gradient, it has velocity, and it has volume behind it. So this is where we get flash floods, really fast floods that occur without warning. So obviously they're most common in the higher elevations. So if we have a small drainage basin, they're really common in urban environments because a lot of urban environments, as we said, we build up those impervious surfaces. We're not going to have good enough drainage. And stormwater management is just basically those steep channels. You're creating something that can't infiltrate anything. It's just directing water, so it'll give it more velocity. And obviously, if we have arid environments and we have very little vegetation, we're obviously not going to get enough interception from that vegetation. So Texas, Southern Cali, we're going to get a lot of those there. Oklahoma, Nebraska, those areas, we're going to get a lot of flash floods there as well. So because of how quickly the water rises and because of how little infiltration there is, we're going to have a very short lag time between the peak precipitation and the peak discharge. So very, very short. It can be as little as 10 minutes. And because it's so short, it's the most dangerous because there's not enough time for warning. You may be able to get the warning out in 10 minutes, but is 10 minutes enough for anyone to do really anything to get out of the area? Probably not. So that's why these are so dangerous. So this is what flash floods look like in California. That's coming right down the road. Great camera work. All I'll say is if you're going to be stupid enough to stand around in a flood, the least you can do is get good shots of it. That's what I will say. But very, very fast flowing water. And it's so sudden that there's no real way to get out of its way. But because of that, because it happens so suddenly, the water is going to leave quickly too. And as it's going to leave quickly, it has so much velocity and momentum behind it, it's going to carry everything with it. So this is in West Virginia about 4 years ago. 4 years ago. Oh my God, we're in 2022. This was almost 6 years ago. Jesus Christ. So this was just 8 to 10 inches of rainfall in 12 hours. And this area of West Virginia gets around 41 inches per year. So they got a quarter of their yearly average amount of rain in 12 hours. So this was incredibly devastating. It's rising above the bridge here, and it's carrying everything with it, no matter how on fire it is. So yeah, this can happen everywhere. This specifically destroyed around 1,200 homes, and 23 people died. So as you can imagine, not only is it going to carry cars and debris away, it's also going to, if it can erode rocks, in zone 1, it's going to erode anything that we build. We build stuff out of rocks. Concrete is just broken down dust of rocks. So if it can erode rocks, it's going to erode foundations. It's going to create, it's going to make the sediment that we've built upon a little more unstable, a little more unconsolidated. So buildings can collapse, tip over. So we get a lot of problems with this. So how many feet of flowing water do you think a car is able to be swept away with? What do you think? 2. Yeah, that's all it takes. It does not take much water to sweep away a car. Just because of that, how fast it's moving, it's able to generate a little bit of buoyancy underneath the car. So it's able to just sweep it away, no problem. So that's why if there's ever flood waters, like let's say there's a road that goes over a bridge to a stream and it's flowing over, that's why you're not supposed to drive through it, because it doesn't take much for you to lose traction and just get swept away. The moment you lose traction while you're driving through flood waters, it's all over. All right, so based on the map, which of these areas is most at risk for flash flood? West Texas, Denver, Delaware, St. Louis, or Seattle? Yeah. Tejas. That is exactly right. West Texas has such an arid environment and it's such little vegetation that they're going to get a lot of flash flood risk. Really high. So as we mentioned, impervious surfaces, if you can decrease the amount of infiltration, if you decrease the amount of interception sources like vegetation, and you're decreasing evaporation, you're going to increase the risk of flash floods. So much like in zone 1, where we have those really narrow stream channels that are just going to funnel water, all of our stormwater management move the same amount of water really, really rapidly. So because there's no friction, it's just like a concrete tube. It's just going to funnel all of that water somewhere, and it's going to have so much velocity behind it because we have develop it at such a steep gradient. So they're pretty devastating if they get overwhelmed. All right, I just gave you the answer there, so we'll skip that. Okay, so one of the other ways that we can decrease flooding is, or increase flooding is, we're decreasing infiltration, we're decreasing interception, and we're decreasing evaporation. So, which is funny because you'd think that if we have all of these surfaces of concrete and asphalt, you'd think we would increase evaporation, but actually not. Because the vegetation of trees and grasses, they soak up so much water, they transpire, and they send so much of that water up back into the atmosphere. So we have around 40% evapotranspiration in natural stream systems, where we have like a riparian barrier of trees and some grasses stabilizing the stream channel. As we start to build, we lower that by around 10%. And at the same time, we're increasing the amount of runoff, we're decreasing the amount of infiltration drastically. Infiltration is probably the biggest one when it comes to urbanization. So all of this stacks up on each other and increases the amount of discharge that we're going to get. Okay, so this is what White Clay Creek looks like. I know it's hard to see if you're here in person, but as you can see from where it is in Pennsylvania, up right there to the northwest, we have some really nice meanders in the stream. And as we know, a natural stream system has a lot of meanders whenever it gets to a coastal plain. So that's how it gets its velocity. So right around that red star, we're in a more of a natural state for the White Clay Creek. A lot of stream meanders, probably much cooler water, low temperature water, a lot of infiltration, a lot of vegetation growth. You can see just by the image itself, a lot of green up there. Now we're starting to get into Delaware, right north of Newark. Now we're going to get the beginnings of urbanization, more suburbs, more farmland, some agricultural parcels that you can see there. So now we're getting a little less and less of a meander. We're not making those real sweeping turns that we used to way up north in Pennsylvania. And then as we're getting closer and closer to Wilmington, we're going to even get more urbanized, more development. Some of these past that blue star, it's almost a straight channel, which will end up being a problem. So this is what we would expect for the natural portion of the stream. So this is probably what if all of White Clay Creek was a natural stream system, this is what we would look like in our lag times. So right up near the headlands, we would get a very short lag time, sharp increase in the discharge, mainly just because of how close it is to the precipitation event. As we go further downstream, we have a longer lag time and a longer lag time. And you can see the shape of that curve is going to become less and less drastic. So as we decrease, the discharge is going to be the same, but as you can imagine, because it's happening so over such a longer time period, we're going to get more infiltration, more interception. So we're not going to get those extreme peaks and valleys that you'd see for a flash flood. Now, this is in a natural stream. This is what we actually get. So we still have for the Red Star in our up north in Pennsylvania, we're going to have our very short lag time, which makes sense because it's closest to the headwaters. It's going to be the closest to the storm. It's going to have the shortest lag time. But the lag times for the Green Star and Blue Star are almost exactly the same because we have so much urbanization. So why is this? Why do you think all of our streams downstream are behaving like zone 1 streams? You just shout it out. It's urbanization for sure. Definitely not overforestation because that would be growing too many trees. We don't have excessive agriculture. We have some farms in northern Delaware, but most of the farmland in Delaware is to the south along the coastline where we have a lot more flat areas. It's easier to spread out in those areas. So Kent County, Sussex County, a lot more agricultural down there. Too much rainfall this year. It would be hard to say if we don't have data for it. So that can't be the answer. So it's got to be urbanization. Okay, so how do we mitigate this? We got to do some stormwater management because people are not going to stop living places. So we have to be able to manage this problem. Otherwise, we're going to keep getting worse and worse floods and not be able to do anything about it. So we want to decrease runoff. We can't control precipitation, but what we can control is infiltration and interception. So if we plant more trees, obviously that's the easiest one. Trees as after you plant them, they're self-sustaining. You don't have an upkeep cost. They don't require electricity. They produce oxygen. That's the easiest investment that you can possibly make, where you don't have to pay for anything after you plant it. However, we can't plant trees everywhere. So in certain places, we got to implement retention ponds. So as I mentioned, a retention pond is literally just a hole in the ground. That's all it is. That's all a retention pond really is. It's just a fancy hole in the ground where all this water is diverted from all of our impervious surfaces. So if you go out to any of the parking lots or any of the streets, you're going to see stormwater drains. Where do you think those go? They're going to end up in a retention pond first. So whenever we get a big storm event, all of that water that lands onto our impervious surfaces, our parking lots, that's going to flow and be redirected through all these channels into a retention pond where the velocity is going to slow down because it doesn't have a gradient anymore. And because it's just sediment, it's going to infiltrate a lot faster. So you give it a place to slow down, and once you slow the water down, that's where you're going to get that infiltration back into the groundwater. So that'll help mitigate the flood stage. Basically, all you're doing is you're buying time. You don't want to stress the stream system so much that it'll overflow. So if you don't have to completely stop the flow, you just have to give it enough time for the precipitation to stop, and then you can send that water back into the stream system. No problem, no flooding. So we do have some retention ponds in Newark. This used to be Rodney Hall, which was recently demolished. Used to be a residence hall. There used to be some pretty bad flooding on Main Street, specifically South Main Street. And as you can imagine, it gets expensive, it gets costly for not just the university, but the city itself, all the businesses on Main Street. The more flooding you have, the higher flood insurance premium that you're going to have too. So it's going to end up helping your costs as well by having some floodwater management. So the Rodney Park stormwater system that they're developing is they want to manage this type of flood event, and they have a goal to reach. They don't need much. We're not going to get a devastating Johnstown-like flash flood, but we want to be able to manage at least 6 inches of water. Even just 6 inches of water flowing down Main Street, that's over your ankles. That's going to be a problem for a lot of people and a lot of businesses on Main Street. So if we can mitigate that and take some of that flow away, we won't have any problems. So this is the entire complex system that's going to flow into this retention pond. It's still under construction. It's going to impact around 185 acres, which is a huge area that's going to capture all of this water from all of these impervious surfaces. And it's going to, the downstream impact area is around 121 acres. And that's a lot of residential areas. As you go further downstream in White Clay, a lot more residences than big population centers. And even further, the indirect impact area, where it's not completely dependent on this system, that's around 535 acres. So like a huge amount of area that can be impacted by this stormwater design. So basically all it is it's just a wet pond that has the capacity to fill up with a large amount of water, give us enough time to let the floodwaters recede so we can open the spillway again and then let that flow back into the White Clay Creek. There's some other benefits to having this type of pond. So anything that flows in is carrying everything that's on those impervious surfaces. If your car leaks oil, it's going to bring that in. If you have anything that is spilled on the street, it's going to bring that in. But these wet ponds with all these marsh type grasses, they're going to soak up a lot of that real nasty contaminants that could end up in the Delaware Bay or in the Chesapeake Bay or any other bay around the world. So this will end up reducing pollution. It soaks up nitrogen, phosphorus. Those are really common in fertilizers. So as you get a lot of nitrogen and phosphorus in like Chesapeake Bay, for example, they had a big problem with red algae. Red algae feeds off of nitrogen and phosphorus. It's real nasty stuff. It chokes up the water around it because it uses so much oxygen. So you get lower amount of aquatic life and biodiversity. So the less the nitrogen and phosphorus that we can get in the area, the better. Obviously, the flood mitigation portion of it, you can store 6 inches of water for 24 hours. That's a 25-year flood, and it can safely manage around 8 inches of water, which it'll probably be at the full height of the pond at that point. But we don't get that kind of flood around here frequently. So luckily that won't be too big of a problem. And obviously there's the aesthetic portion of it. It does support aquatic life, so you can go fishing in it. It's catch and release. It's nothing big, but it's still fun to do on an afternoon. Obviously there's a park around it, so some walking trails, some hiking trails. So it benefits the population as a whole. Now, we get to the problem that most people care about. It's not free. It costs a lot of money to do something like this. So this will end up costing $26 million in taxpayer money. So how do I put this? This is the initial investment, $26 million of your money as a Delaware taxpayer. However, if you think about if you're a Delaware business owner, you have to have flood insurance. If you're a homeowner, you have to have flood insurance. And if you have frequent flooding, your flood insurance premiums will go through the roof. So an initial investment of $26 million from the taxpayer could end up saving you money over the long term. And that's the problem when it comes to stormwater management system. It has a high price tag, but the benefits from it from a long period standpoint, if you plan to be in the area for a long time, it's going to end up costing you a lot less money. So this is what that looked like. That's El Diablo Hot Bagel Roots Kitchen right there. So that's what it looks like during a flash flood 4 years ago. Luckily, we don't get the kind of floods that they get in Iowa, but if we keep getting more and more precipitation events and we don't have any stormwater systems, this could be a huge problem. Okay, so now let's start looking at zone 2 and zone 3. So this is the Mississippi River. As you can imagine, the Mississippi River being the largest river in the continental United States, It's got a lot of stormwater management practices along the entire length of it. So it's a pretty humid environment. Most of the Mississippi River, very humid. Since it's such a flat area, we have these large floodplains because of this huge meandering river. And all the tributaries coming into it, they're also huge and meandering. So we have huge floodplain areas, which means we have huge areas of just flat elevation that could easily be flooded. And then, of course, because it's the Mississippi River, it's a huge economic area. A lot of shipping is still done up the Mississippi River. We have a lot of urbanization around it. People want to live where their jobs are, of course, so they're going to live near the river. And obviously, because it's such a huge source of water, we're going to have a lot of farming nearby, a lot of irrigation in that area, sustaining a lot of farms. You guys ever tried talking for almost 2 hours straight? It's really hard. It takes up a lot of saliva. Okay, so for downstream floods, obviously we're gonna have a longer lag time. And this is in natural conditions, keep in mind. So because stormwater is coming up from the headwaters, we're gonna have a longer period of time in between where we start to see the peak discharge and the peak precipitation. So a lot of the problems from downstream floods, we have long duration storm events, and we have all of these tributaries feeding into this zone 2 area. Remember, it's not just one river. Rivers are fed by all these different tributaries, so we're getting the combined runoff of all of those tributaries. And also, since we're at such a low elevation, we may have so much infiltration that the soil gets saturated. And remember, if we reach that saturation point, we can't infiltrate anymore. It's going to flow over the land. So these ones, we don't get flash floods in these zone 2 areas, but they do rise slowly, steadily, and predictably. So we're able to kind of account for these and plan for these a little better. So they'll continue to rise long after the rain has stopped, mainly because of that lag time. And we get the huge amount of accumulated discharge from these tributaries all the way up in zone 1. So while they rise a lot slower, they could still potentially be pretty damaging from a property aspect. Probably not going to get swept away by these, but it could damage your crop yield or anything like that. So obviously, if we have alterations to the floodplain, such as increased erosion from farming, we're going to have less interception. So like these are cornfields in Indiana. Obviously, in the months of June, we're probably going to have a lot more interception, a lot more infiltration because of the corn yield in that area. That's a huge area of vegetation. Even though it's not natural vegetation, it's still going to soak up a lot of water. It still has the potential to soak up a lot of water and direct that water. So in the summer months, we're probably going to have less amounts of floods. In December in Indiana, they still get a lot of snow. So we're going to get some permafrost, we're going to get more ice. We have the potential for less infiltration, more runoff, bigger, higher floodwaters in this area. We can also alter the stream channel. So if we keep eroding stuff away from like farmlands, for example, we're going to build up a lot of sediment in the stream channel. And as you can imagine, if we keep building up sediment, remember zone 2 is the area of transport and deposition. So we can build up a lot of sediment in these areas. So if we increase the stream gradient, we're going to increase the velocity. And if we increase the velocity, we're going to keep eroding and down-cutting stream beds, and we're going to erode and down-cut these stream walls too. The walls are what's keeping the floodwaters at bay. Okay, so what's the solution here? Wetlands reclamation is a really important thing. Most people are starting to realize there is an economic value tied to wetlands as a whole. It's difficult whenever you're working with earth science because most people think in dollars and cents, and it's a lot easier to explain things in dollars and cents. So if you talk about like wetlands reclamation, they care about the initial cost, but if you're able to calculate saved cost to that, you're going to be able to convince a lot more public policymakers to enact more environmental solutions like wetlands. I used to work with wetlands a lot for my master's. I did a lot of work in Slaughter Beach, Delaware, with the coastal salt marshes. We'll talk a little bit more about coastlines, I think next week or the week after. And salt marshes are really, really important ecosystems for coastline management and preventing floods and stuff like that. But we also have freshwater wetlands. As we've said, they work kind of like a retention pond. They're areas that can take in and soak in a lot of water. It acts like a sponge. Obviously, they have so much vegetation. They have these long grasses, trees that can handle a lot of water, so they're going to intercept a lot of that water. Because you have such, for wetlands, you have a lot of grasses. Grasses have the largest root systems. Even though the grass in your lawn is probably no taller than that, their root systems are feet and feet deep. So they can hold the soil together a lot better. So we're going to prevent a little bit more of erosion. It acts as a barrier. It's going to slow down that water. And if we can slow down the water, decrease the velocity, we're going to increase the amount of infiltration. And of course, just like with our retention pond example with the Rodney Park retention pond, we're going to reduce pollution. Can soak in all that nitrogen, all that phosphorus. So the more wetlands you have in an area, the better water quality that you're going to get going back into the stream channel. So what do you think is going to make redeveloping wetlands a problem? It requires people to change how they're using land. They can be controlled by different states or national governments. The species in this area may no longer be able to live in these areas. So what do you think it is? It's all of them. Yeah, it's the biggest problem with developing wetlands. It's really difficult just because there's so many moving parts, and obviously, if I was a farmer, I wouldn't want people coming in and saying, hey, I need you to take away some of your land to put it to this use. So I don't blame them for that at all, but hopefully that we as scientists can figure out ways of showing the cost benefit to developing more wetlands reclamation programs. It would be really beneficial in the long term for a lot of flood hazards specifically. Okay, so another alteration that we can make to the floodplain is levees. So you all know that levees are man-made structures built as like a wall to the water. So in a normal system, in a normal zone 2 system, we have this meandering river. It's carving that natural course. It's as wide as that normal floodplain. So we're depositing stuff on the floodplain. We're cutting, we're merging and finding new pathways into the river. So sometimes they make their own natural levees. We mentioned that as the flood comes over the banks of the channel, it deposits a lot of that sediment along the sides of the banks. So it makes kind of like its own levee that way, but that takes a long, long time to make. And obviously we have these wetlands developing along this floodplain because the soil quality is so good. So we have all these different natural systems going in tandem with each other, finding a balance. So if we introduce levees to that system, we're going to fix the course of that river. So the course of that river is not going to extend past those built levees for now. But if we have flood events, we're going to start to remove moisture from wetlands. And remember, if we're drying out these wetlands, we're going to get rid of that vegetation, less interception, more runoff. So this could become a problem. So levees can help you build on flat areas, but as you can imagine, if you are creating a bottleneck of some structure, you're going to get a greater velocity, greater stream energy, and if you have more energy, you're going to have more erosion. So something that the first people that started building levees along the Mississippi, they were calculating the velocities of the stream, just like we did when we calculate discharge and everything. And they developed some type of engineering plan to go into place to account for that velocity. What they didn't understand was that as you input changes to the channel sides, you're going to get an increase of velocity. And the structures they built couldn't stand up to that increased velocity. So they started eroding the levees that were built themselves. So it ended up being a stupid expensive project that didn't work. So another thing that you can get is, we measured the bottleneck effect. So it's almost as if it's a damming effect where you get a buildup of stuff behind the construction. So that can also lead to flooding because you can't build levees along the entire length of the river. That would be just unnecessarily costly. So you have to pick and choose areas where levees are best suited. So areas in the back that aren't protected by levees could end up getting flooded more frequently because the water has been backed up behind those levees. Okay, so this is the Mississippi River near St. Louis. So this is the point where the Missouri River and the Illinois River flow into each other right here at Alton. And all of those red lines that you see are levees, engineered levees that we've built. But keep an eye on where those levees are. Now think about these floodwaters and where they are. So remember in St. Louis, huge population center, huge amount of urbanization. They have the largest levees in that area. So you'll notice nothing flooded in St. Louis at all. But everything upstream of St. Louis experienced a lot of flooding because of that huge bottleneck effect. You had this buildup of everything behind it. So everything spilled over the walls. So that's the problem when it comes to levees, seawalls. We'll talk about seawalls when we talk about coastlines and climate change. You end up having to pick and choose what's going to get flooded and what isn't. So I've mentioned this in class before. Water is one of the most powerful things on Earth. It can cut through anything if you give it enough time. If you give it enough velocity, it will erode anything. And that same thing can happen for stuff that we build. So they can find so many different weaknesses in levees that we build. So there could be what's known as piping, where it finds like fractures in the structure itself, where it can start to erode away. If it can flow somewhere, water is going to carry stuff with it and carry stuff away with it. It can get high enough that it can find a breach, and once you have a breach, you increase the velocity because you have such a steep gradient on the backside of the levee. So that's going to continue to cut away and make it even worse. You can also get stuff that gets underseeped. So you can build up the levee as much as you want, but if you're building it on top of, say, like sand, the water is going to soak into that sand and it's going to flow. If it has enough velocity and enough pressure potential, it's going to flow underneath it and seep upwards. And then if it seeps upwards, it can't get out because you've built a levee there. So you have this problem of sustained periods of flooding where you would have to pump everything out. And you'd have to wait for the floodwaters to recede at the same time. So time and time again, water always wins. This is the 17th Street Canal in New Orleans. On the left, right before Hurricane Katrina, you know, this beautiful canal connecting a lot, running through some residential neighborhoods in New Orleans. Right after Hurricane Katrina, we had such high floodwaters that the levees obviously broke. They cracked. Some people described it as hearing like a cannon go off. That's how much force was behind it. And then it just flooded into these residential areas and really, really devastated New Orleans. So if you give water enough time, disturbance, and gravity, it will obviously take out whatever you put in front of it. So obviously, whenever you're building levees, number one, they have to be high enough. Remember when we mentioned tsunamis, how they built seawalls that were so high, but the land subsided that the water just poured right over. Similar thing here. You're not going to get a lot of subsidence from floodwaters, but you have to account for the amount of potential water that's going to flow through there. So if you don't build it up enough, then that's going to be a problem. So this one is actually from the 2011 Missouri River. This is in Hamburg, Iowa. So they had two levee system. So they had a large levee that you see here that breached. And then just in case there was any seepage, any potential small overflow, there was a much shorter levee on the other side, protecting residential neighborhoods. Because they had such a huge breach in this one, the levee on the backside wasn't big enough at all. So it just flowed right in and just devastated everything. Okay. So here we're measuring stage. This is another hydrograph. This is from NOAA instead of the USGS. So let's test ourselves again. What's this? We have up here, we have information on what the flood stage is. We have time on our x-axis. We have the actual measured stage on our y-axis. And we have our actual data here in blue and then in purple. So what's the flood stage of the Missouri River at this specific site in Nebraska City? Yeah, that's exactly right. This is a reading exercise. It says 18 feet right there. It literally will tell you the flood stage for each of these stream gauge sites. So it will tell you when it's going to be in flood or not. So it is 18 feet. So is the Missouri River at this specific moment above, below, or at flood stage? This is a graph reading exercise. What's that? It's above. What do we have on the side here? We have about 21.5 feet. At this point, it's at 20.3 feet. And even at the end of the day on Friday, November 1st, we're still above 19.5 feet. If the flood stage is 18 feet and our actual stage is above that, we're experiencing a flood. So obviously it's above. All right, how about this one? So what's the flood stage? Where is it right now? Is it below, at, or above? That's exactly right. Flood stage, 25 feet. Everything on this graph is below 18 feet. So obviously we're not at risk of a flood right now. They may have had some precipitation, it looks like, but it looks like that's starting to discharge. That's not going to be a problem. Let's see. Okay. So we've talked about this, we talked about this. And we talked about levees helping, but also hurting. Okay. Real quick, let's talk about zone 3 floods. Obviously, zone 3 is where we have our areas of deposition. We have the lowest energy velocities, lowest elevation, lowest gradient. So already we have a lot of uncertainty when it comes to flow paths and where the water is going to go. So in zone 2 and zone 3, we have really well-defined stream channels. So we kind of know where the water is coming from and where it's going to end up going. Because once we start to exit out and we have stuff built up on these deltas, we have no idea where it's going to go. There's so many different variables. So this is a case study of the Atchafalaya River back from 1831. So they wanted to dig a canal to kind of save a little bit of time, a couple hours. So instead of going 20 miles around the bend, you go 1 mile right down this canal. So instead of, it's basically creating a man-made oxbow almost, where you're just directing the water across that little peninsula so you can save some time. So eventually what happens is this, this diversion of flow is going to create a preferential direction. So because of this, all of this flow ended up going into the Mississippi instead of the Atchafalaya River. So we decreased the amount of flow in this river. We ended up decreasing the population, and it just blew up this this area of Louisiana. It was absolutely devastating. So they had no way of planning for this distribution. Okay, just to test you guys again, how do we calculate gradient? What is gradient? Well, what's another word for gradient? Just shout it out. Slope. What's slope? Rise over run. Okay, so we have two different rivers, the Atchafalaya and the Mississippi, and we have the same starting source, Simmsport, at 30 feet, and we have Morgan City at 0 feet, New Orleans at 0 feet, but the distance between the two is different. So how do we calculate that? And what do we end up getting? Yeah.
About 0.19 miles per hour.
Mm-hmm. Very good. So how did you get that?
You just take the rise of the elevation of 30 feet to 0.
That's exactly right. Yeah, well done. Okay, so we have the same rise. There's our elevation change, 30 to 0, so 30 feet. And we have a different run, different distance. So as you can imagine, if we have a smaller distance, we're gonna have a greater gradient if we have the same elevation. Okay, all right, that's all I have for today. I figured instead of taking a break, we just breeze right through that. Don't forget your assignments on Canvas, quiz 3, and there's also an in-class exercise that'll be due next Wednesday that's up now on Canvas, and that's going to be on flooding. Basically, you're going to go on the USGS site, you're going to pick your favorite stream. If you have one from your hometown that you're familiar with, there's probably a gauging site there, and it's going to ask you to give me a lot of information about it. So all that information is on Canvas. Please get to that. And if you have any questions, let me know. My office hours are Tuesday and Wednesday, but I'm available the rest of the week if any of you need help or want help studying for exam 2. So that being said, have a great day, everybody. I have 2 people that have to take it, one today and one Monday. So I'll probably have your grades and go over exam 1 on Tuesday. Okay. So most of them are graded already. Just have a couple of them. I can't go over it until they've taken it. Bank full stage? Yeah, bank full just means we haven't gone over the levees yet. So bank full, it's like the max capacity that the river can take before it floods. Anything above that, it's flooded. You too.